right, so for the plan for today, this will be our final lecture about divide and conquer algorithms, our first algorithmic design paradigm. And this algorithm is actually going to be one of the cleverest we'll see of. It's going to be a linear time algorithm for finding median, or more generally solving the selection problem. So it is a divide and conquer algorithm, but it's one to which does not apply because it makes different recursive on different. Along the way, we'll also have an excuse to introduce a different analysis method called the substitution method, which will allow us to prove the linear time bound. Okay? So most of you have seen the selection problem before. The input is just like for a sorting problem. So we're given as input an array A, but then let's say they're integers and let's say they're distinct. And we're also given a number I, where I is an integer somewhere between an n, where n is the length of this array A. And the goal is to compute what's known as the ith order statistic, or the ith smallest entry of the array. So for example, if you were passed in I equals 1, it would be asking you to find the minimum, not a hard problem. If you pass in I equals, asking you to find the maximum, not a hard problem. If you pass in I equal n over 2, then you're being asked to find the median. Okay? The minimum and maximum, of course, I'm sure you all see easily how to compute linear time. Median's less clear. However, I hope you do see a way to compute the ith order statistic for any I, in particular the median in n log n time. Who can suggest how to solve this problem in general with an algorithm that runs in time? Yeah.
Just merge it with merge sort. Sort it with merge sort. And just take the I.
That's right. So the proposal is to just sort the array, and of course we know how to do that in n log n time. For example, using merge sort, which we saw last week. Then once the array is sorted, pretty obvious what the smallest element in the ith position. So just return it in constant time. Okay. So one way we could get a better than an n log for the selection problem would be to devise a sorting algorithm which is better than n log n. It turns out sorting algorithms better than n log n do not exist, at least in the so-called comparison model. You can find an argument of that lower bound at the end of handout number 6. I hope to have time to prove it in class in maybe a week or two. Okay? So if we insist on solving the problem by solving be stuck. A mantra I want to instill in all of you is whenever you see a solution to a problem, you do better. So for could we do better? And today I'll show you that the answer is yes. Okay, and so we using a quite clever divide and conquer algorithm. Okay? And of course you do need linear time. I believe this was discussed on courseware a bit. To find the maximum, you would need linear time.